Okay, welcome to another hour with Dr. French. This week it's on chaos, and the competition is going to be released this evening. There'll be more information. It's not going to be released, and that's the end of it. There'll be lots of information forthcoming if you stay with us. And what you'll see is it's not on chaos or some of the other topics that you've been looking at. They're about examples, how you might go about sort of presenting some interesting ideas and doing some programming in those areas. But you can transfer those skills and those ideas to the actual competition. So make notes on this, look at the ideas that are presented and how they're presented, and then you can do similar kinds of things or think about doing similar kinds of things for the actual project that is to come. So welcome, Dr. French.
Right, and good evening, everybody. We are coming to the conclusion of this year's computational challenge. For those of you who've been to every session, fantastic. If this is your first session, you're very welcome. This is going to be all about chaos. Hopefully the session won't be chaotic, and I'll explain what chaos actually means. It actually really means complexity from well-defined rules. So speaking for this, let's look at some well-defined rules of this year's computational challenge. So I'm going to duck out of this and look at my other presentation, which is, da-da, the 2025 challenge is on waves and optics, actually optics and ray optics to be precise. So this year, there's a couple of changes. We're going to go for 3 minutes for the YouTube video, which is what you present with your solutions to the challenge. What you're going to get very shortly, hopefully within the next few days, is a short 2-page document which kind of outlines all the tasks and how to do it and how to be successful, etc. And then you'll get a big document, which is this one, with all the recipes of what to do. Basically, and you can use any coding language you like. And in fact, we're really sort of thinking about sort of like how to get into people at the bronze level who may not have done any coding at all. So there's quite a few things which you can do very successfully with just Excel. And then we've got a kind of series of thresholds. So basically, there's lots of things at the beginning where you're plotting curves, that kind of stuff. And then we've got a kind of animation idea where you're manipulating bitmaps. So although it may seem like we're giving you quite a lot of tasks to do, it's actually kind of the same thing with different sort of lenses, if you like, literally. That sort of ties in with what people have done in the past. They've often made a kind of app or website or whatever that does multiple tasks. So we've kind of gone with that, really. And then the last bit of the challenge is a bit of modeling. We're going to look at rainbows, so rainbow physics. So this is big dollop of this is what was in the Science by Sim 1. We're going to give you all the theory for it, and also some prisms as well. And just for fun, there's something rather pretty on anamorphic images, which I hope you'll all have a go at, practically as well as with software. So if anyone fancies actually filming that in the real, we've never had someone actually putting some live video in a BFO challenge. So maybe this is your opportunity to. So let's just have a quick tour through some of the things. We won't look at all of them, but I'll give you an idea. So basically, there's lots of text here, but you've got to submit a 3-minute maximum, and we are going to be very strict on this YouTube video. That doesn't mean you do it at double speed, all right? We can tell. So probably the hardest bit of this challenge is actually telling your story in 3 minutes. Well, if pop stars can do it, then I'm sure you can. So there we go, 3 minutes maximum. So what's the first part? So challenge number 1A is to plot the refractive index of crown glass. So you mean the refractive index is the speed of light in a vacuum divided by, the speed of light in a medium is the speed of light in a vacuum divided by this thing called the refractive index. So this is very particular to light. It doesn't really work for sound because we have this sort of speed limit for light. It's quite interesting. It's actually a sum. So I've defined it in terms of a for loop here. This is called the Sellmeier formula. And that's quite easy to do in programming. This is literally how you do it in MATLAB, but you could do it in Excel. There are these sort of coefficients that you have to use, and you use a loop, and it's a sort of something squared over something squared minus a constant. All right, so it's not a trivial kind of formula, something that really lends itself to doing with a spreadsheet. And you end up with a curve that looks a bit like this. So this is over the visible range, or just about. So a similar one is slightly harder, is to plot the refractive index of water versus frequency. And you're going to need this in the later parts of the challenge. So latter parts of the challenge, the models of rainbows, etc., and prisms kind of involve the bits that you do at the beginning. So it's a kind of bit more interwoven. So this is the nice graph we'd like to have a go at, particularly this bit in the middle, and is to actually sort of plot a very nice, more professional looking graph with the color coding automatically. So this is something you do in Paint. This is something you need to actually plot. This is a very visual piece, is this year's challenge. So there's a little sort of snippet. So this one, for example, the refractive index of water, basically we have a sort of formula for this. There's a sort of formula for it in the top of the graph. Again, it's not something that's particularly trivial. It's actually an empirical formula based on some curve fitting. So that's the refractive index of water versus frequency in terahertz. So you can get used to plotting graphs, maybe with a nice title. That's something you can easily do in Python, Matplotlib, MATLAB, whatever, you know. And of course, you could do all of this in Excel. But you've got some interesting criteria here for plotting the colors. And I give you the RGB indices for violet, cyan, orange, and that kind of thing. So that's something that you could use a lookup table for. Again, all of this can be done in Excel, but it's perhaps more interesting to do in programming. So how does that develop? Well, I know we've got something a bit different, a bit of experimental physics. And again, I would highly recommend doing this Excel. And you've probably, I hope all of you have done something like this. This is our version of looking at the law of the lens. So here's a biconvex lens. And as you know, for an ideal lens, horizontal rays go through this place called the focus. They don't stay there, of course, but they all pass through that point. And you can figure out what the focal length is via this rather lovely formula. So if you look at the sort of picture at the top left, here's a biconvex lens. We've got a ray box here and a screen. And the lens to ray box distance is U. The lens to screen distance is V. And they sort of add in reciprocals, which is rather cool. And you can derive it from, well, the laws of the lens. And I'll let you ponder that one in slow time, but it's just looking at straight lines and that kind of thing. And so I've given you some data, some actual experimental data, which I took in my lab. And this ray box produces a big F, not F for French, but there we go. And you see an inverted F in the corner. I'm not sure that's going to come out in this talk, but the idea is you sort of move the lens along the ruler till that your image is in focus. It's a very good simulation from PHET called geometric optics, which explores basically the same thing. So the idea here is you're trying to work out from the gradient of 1 over V versus 1 over U what the focal length is. So you can work out that. So that's a nice thing. And of course, if you do it in programming, you could work out, implement a line of best fit function, something like this. Or you could just use Excel and do that. So there's loads of options here from sort of, never done any programming, use Excel, processing data, following that flow and writing it up, all the way to ingesting data in a completely programmatic way. All right. Okay, so that's the kind of intro start. There's a little diversion, which is about plotting curves. And this is some really interesting ideas based on Pierre de Fermat. And so, we're looking at the law of reflection, so A to S to B. And we know that those angles are the same, but why? So Pierre Fermat's principle basically says, if you work out the path from A to S to B, and that could be not in the middle, it could be anywhere, and work out the time. So this is a bit of Pythagoras. You're working out the time from A to S to B. And if you plot that versus the distance between A and S horizontally, you get a nice curve. It's not quite parabolic, but it's sort of close to it. And if you sort of work out the sort of minima of that, well, what you find is that minima corresponds to those angles being the same. And you can do a bit of calculus to prove this, but in the spirit of this challenge, this is all about computation. So that's quite nice. And then what the second part of this is to do it for refraction. So there we go. That's the maths of it. I'll let you have a look at this when you download the presentation. But you get a very similar situation for refraction from A to S to B. In this case, we're going from one media to another. And these are two different refractive indices. And so you, again, work out the time it takes from A to S to B, parameterized by distance x. And you plot a graph, find the minima, and you discover at the minima that n1 sine theta is n2 sine phi. which is Snell's law. So there we go. Stuff you've been using probably for years, but why is it true? We can do the minimum of the time of flight, which is rather lovely. For those of you who might be reading ahead, that's also a special case of Feynman's sum over histories method. I probably don't recommend doing that, but it's possible. You could look at all directions and it goes at once, and this one is the most probable. So that's how we go from Fermat's kind of idea to much more modern quantum electrodynamics. But there we go. So that's the kind of starter stuff. And then we get to the kind of the next phase. So all of the previous parts are accessible with Excel and very basic programming. This, I think, is you do need to do some coding. So if you want to get a gold, we want to see most of the challenges attempted. A good silver could you tried some programming, but this is the kind of sort of threshold. So essentially, what you have to be able to do is read in a bitmap image and display it on a screen. So I've got this little bitmap of. So who is this person here, by the way? I want to put that in the chat. Yes, it is. It's not Schrödinger, I'm afraid. It is Maxwell. Well done, Arjun. Yeah, that was very quick off the mark. So there we go. Whose Maxwell's equations, the four of them define electromagnetic waves, or electricity and magnetism, in fact, the fields themselves from charges and moving charges. So this is a bitmap, which she says ray optics on it. So you can create your own. Maybe nice. You can have a picture of yourself or your cat or whatever. And they were displaying what happens when we transform that in a mirror. So this is just a sort of reversing the x coordinates. But the guts of this is really how you can load in an image and do something with it. All right, and of course that unlocks computer games, usage of graphics, all sorts of things. So you can certainly do that in matplotlib, and probably lots of other languages too. But I think that might be a little bit of extra work if you've never done this before to figure out that. Once you've got this mastered though, then you can do all the others. Because what we're going to do is transform the XY coordinates. And now this is a very simple transformation. It means literally swap the sign of the X values, but we could do something more interesting. And this is what happens when we look at the lenses. So for a thin lens, this is my object and this is my image. And these are the transformations. So X comma Y, that's where the green spot is. And little x comma y is the red spot. But of course I can do that to every single coordinate that makes up my bitmap. And I end up in my inverted, slightly distorted image. And these are the transformations which you get from the thin lens equation. You can do something similar when you're having a virtual image. So that's where my source is, my object is between my focus and my lens. So there we go. I get an enormous version of Sybil the cat as a virtual image. And it's a very similar transformation, of course. So maybe you could combine the two. Indeed, that's what the PHET simulation does. I'm afraid my one doesn't that produces this, but perhaps yours can. You could have a special case where maybe you move, you could have a mouse pointer or maybe make an app on a phone. That would be really cool. So you could move the object dynamically with your finger and the image is worked out in real time. So that's the kind of thing, if you want to knock on the door for applying for top 5 and you could make an app that does this, that would be amazing. So that's the kind of progression that we could be looking at. But certainly just by plotting it in a static way, that would get you well on the way to gold, I think. So other things we can do. So this is a really fun example. We have a mad mirror. I have this in my lab right at the moment. And I think this is from a searchlight from World War II. It's a huge sort of concave mirror. And you might, if you've been to a sort of amusement park, you might see some of these. There's a place on the Isle of Wight where I was born called Black Kang China. They've got loads of them. And you could have a lot of fun by seeing yourself looking very distorted in the mirror. So what we do is we hang a dinosaur sort of in front of the mirror. And if you are stand about 2 meters away, what you see is the inverted dinosaur, so the right way up, kind of looming towards you. And amazingly, it's actually a real image. Okay, so this is basically what it looks like. So if you take the red spot on the top of Maxwell's head here and go horizontally, the normal to that point goes to the little spot here. That's the center of the circle. So I've got a section of a circle here which represents my mirror. And these angles are going to be the same from the law of reflection, which you've already investigated earlier. And so my image is going to be along this line here. You can also go directly through the mirror of the middle of the sort of the curvature of the mirror, so this sort of center of the circle, and you're going to get a bounce off this point, so it's radially. There's no angle of incidence. So the convergence point of those paths is where the image is. And if you work it through, and that's you could do that, but you could just use the maths. It's a more interesting transformation. It's very non-linear, and this is what transforms little x and little y, which is this point, or a and b, into big X, big Y, which is big A, big B. All right, and you've got some inverse tans and stuff. There we go. So that's a nice thing to do, and then you can do the same for a convex mirror. So basically, all the last sort of 5 or 6 challenges are basically the same thing. You probably have an app, and you might have some sort of lookup table. Is it a convex mirror? Is it a concave mirror? Is it a lens? Blah, 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 right? You could kind of have a general purpose sort of optics workbench for that. All right, so that's the kind of the meat of the challenge. Then there's a little fun bit, which is simpler to code, but really good. This is called an anamorphic image. So if you can acquire a little bit of a kitchen, a sort of a curtain pole, that's highly recommended. So this little cylinder here, I guess you could probably make one of foil, but it's better if it's metal, that you can kind of buff up a bit. And what you do is you take an image and you stick it inside a circle. And the bottom of the circle, the little red spot here, becomes the center of an arc. So in my case, I've got an arc width of 160 degrees, but you can go all the way around if you wish. And then what we're doing is we're transforming the XY coordinates of my image. Let's say, a 1,000 by 1,500 pixel image into this arc. So every pixel coordinate, I've got a color, and I've transformed it. And what you do is, if you actually put that on some sort of tablet, as long as it's flat, you can actually make a sort of 3-dimensional image. So that's me. And it's not bad, actually. You can kind of walk around it, and it seems like it's floating in space. So that's quite a cool thing to do. It's called an anamorphic image. And then the sort of last part of the challenge, the sort of most physicsy bit, I suppose, is a sort of an investigation of rainbows. So there's all sorts of stuff here. Again, this would be a talk in itself, but I'll give you just some ideas. So let's start from, so basically, here's the sun. And what you do, you've got parallel rays, and they will reflect internally off the raindrop back to your eyes. And this is the kind of geometry. So alpha is the angle of the sun. And what we want to relate is this angle of elevation to the angles that the rays of the sunlight hit the rain droplets. And if you sort of go inside the model, this is for a primary rainbow. You get a bounce internally, an internal reflection. And it turns out you can work out the angle of elevation versus the angle of incidence here. And that will be anything from 0 to pi over 2 radians, right? Because there's a lot of molecules and they're very small. And what turns out, if you plot epsilon versus theta, this is for the double rainbow, you get 2 bounces, you get some graphs. So you have to use the refractive indices, because it does vary with color. And what you do is you get the elevation angle versus your angle of incidence. It turns out, and I plotted different lines for different colors based on the refractive index, there's some nice maths involved, and you get peaks for the primary rainbow and a trough for the double rainbow. And at those minima, what you've essentially got is a focusing effect. So for a variety of angles theta, you've got basically one angle of elevation. So in other words, that's another way of thinking about a focus, a lens. All right, so you're drawing light from different angles, and you're ending up at a certain angle of elevation, which is why we see the bright arcs. So and you can make some nice curves by plotting each curve with a different value of n depending on the color. So that's the kind of thing. You could do this all in Excel. I've certainly done it myself. It looks a bit complicated, but that's the Excel sheet. So even if you're going for bronze, you could certainly have a go at this. But it's much nicer if you do it with a programming language. And then, this has got a nice output. So this is the actual angle of elevation of the maximum versus frequency. And you find it's about 42 degrees. See, that number comes up again. It's a bit more for the secondary rainbow. And you'll notice that the colors are inverted. So next time you see a rainbow, the secondary bow has the reverse colors to the other one. And then lastly, we've got this sort of idea, I'm going to skip ahead of it, of a sort of model of dispersion in a prism. A nice thing you can do is make this animated. So you have to basically ray trace this, and I give you all the maths for it. But you can make a kind of dark side of the moon picture. So there we go. So we've got some stuff on rainbows and prisms. We've got a whole bunch of stuff about lenses, which is like transforming an image, and then a few intro things, which is about plotting graphs and using Excel for analyzing some optics data. So there's kind of those 3, possibly 4 stages to this, which I would encourage you to combine. So there we go. That's the challenge. There's obviously lots of extension opportunities as well, which I think I've got here, like graphical user interfaces. Maybe you could write a little paper on some of it. And maybe you could, I've also got something on short and long sight here. So this is a flask of fluorescein. If I've got, so yeah, here we are. You can kind of see, I've got a better picture. There we go. So you've got light here converging in the middle. So perhaps you could make use of, refraction, etc., to actually plot these rays. Could you have a dynamic model of this that could be like an eyeball? That's something, that if you want to really sort of push this, but that's beyond the sort of scope of the basic for this. So do we have any questions about the challenge? I'll leave this one here.
No, we've been answering everything.
Oh, amazing. Well, that's great. So in that case, so that's going to hopefully be released in a couple of days. I will also put it on my website as well, with access to all the other things. And I'll also give you some, I'll send some links about some Excel and Python and MATLAB how-tos and some points of departure you can go from there. So yeah, and it will be due. I don't think we've quite settled on the date. Last year it was sort of mid-August. It might be about a week earlier, but it's going to be August. So you've got several months to have a go at this, and it can be done individually or in pairs, but not 3s, please. I think that would be too many. Yeah, some of our we've had success for individuals and for pairs. I think in some ways, I think pairs is a good thing to do because you can then collaborate. You might have slightly different, an overlapping skill set. You can teach each other and, motivate each other. So that's just a nice thing to do. So there we go. That is the challenge this year. Good luck. So what we're going to do, I'm going to come out of this and we're going to have a little look at chaos. So, okay, so a little introduction. Right. So this goes, the genesis of this talk was one I did a few years ago called A Computational Cookbook of Chaos. And it's based on an amazing book by James Gleick called Chaos, which I highly recommend reading. But, that inspired me to kind of make simulations. And if you like, that's probably the genesis of this whole course. So, if you read something or study something in class, think, oh, can I code that up? Can I make myself a model? And then you are much further down the line to becoming a useful physicist because you can then do something with that information. Right, so we're going to look at just a couple of these things, but there's a whole bunch of stuff which is called chaos theory. So the things I've sort of I've highlighted: the logistic map or maze bifurcations. We're going to use some bunnies. There's something called the Lorenz attractor, a strange attractor. That's probably how much time we've got, but maybe we could. There are other things too: the Sierpinski triangle, Barnsley fern, Mandelbrot's, all sorts of things. So. Yeah, you can access this talk from all these slides from the website if you want to know more. Okay, so firstly, let's just have an idea of what chaos is. So if you think about it, dynamics, Newton's second law, mechanics, what does that really mean? Well, basically, we're trying to predict the future or understand the past. Physics is great. We're clairvoyants. But we don't just sort of, look at entrails or, divination. We write down equations and we try to solve them. And for some systems, that is spectacularly powerful and accurate. So, for example, the movements of the planets around, or the movement of the moon around the Earth, we know to exquisite precision to millions of years in the future. All right. And in fact, we know the moon is moving away from us. The rate our sort of fingernails grow. So also we need, we could predict something about what the Earth is going to look like in terms of tides in millions of years if we survive that long. And indeed, what might have happened millions of years ago. We'd expect bigger tides, for example, which might be a main factor which drove the evolution of life. So in other words, but how do we do this? So basically, if we know the position of an object and we know its velocity, it's its momentum, and if we know the forces on that object, we can basically predict the future. All right, so that's Newton's second law. Mass times acceleration is vector sum of force. And if we know acceleration, we can integrate to make velocity and integrate to make position. However, easy to say, not in practice easy to do when we have complicated forces. And indeed, you may have heard of the book, The Three-Body Problem, which is actually the four-body problem, really. We can't solve analytically more than the two-body problem for gravitational-like forces, inverse squared laws. So if you have, two suns and a planet, you have to use a computer. It's an imperfect solution. If you are interested in more of that, we had a session on that I think it was might be in our first session, in fact. So there we are. Our model works very well for tides, etc., but not very well for weather like this. Certainly not for playing pool. So if you hit a cue ball and the break is always randomized, that's because a tiny error in your cueing will result in a completely different set of outcomes. Right? If that wasn't the case, pool would be very boring as a game. So, in other words, most systems can't be solved exactly, and you need a numerical method. And unfortunately, the outcomes are often highly sensitive to our initial conditions. Okay, so there we go. This gentleman here is called Henri Poincaré, one of my favorites. And non-linearity in our equations, things that are not proportional to x or time, is often the source of all this complexity. So let's look at this maybe a little example. So there's a whole bunch of characters in this story. This is Robert Shaw of the Santa Cruz Chaos Cabal. We're going to meet his model in a bit. I'm just going to skip over this one. So a couple of characters you might have heard of. So this is, when we talk about the Lorentz attractor, that's Edward Norton Lorentz, who's modelling weather in the sort of, what about the 60s, I think, something like this. There's Henri Poincaré, and there's a guy called Simon Laplace, one of the great French mathematicians. And basically, he was saying, well, if we know position and momentum forces, we can predict the future. That's a deity that knows all this information could do it. The trouble is, you can't. You'd have to have infinite computing power to achieve this. All right, and non-linear systems, even their teeny tiny errors can result in very, very different outcomes. So there we go. And also, fundamentally, I've got Werner Heisenberg here. For particles, small things, they obey the uncertainty principle. Standard deviation of momentum and times the standard deviation of position is bigger than or equal to h bar on 2. So in other words, we can only know things approximately. Right, so I'm going to start off with a simple example, which is this one here. So this is Robert May, and he did all sorts of fun things. It's also the same name of the person who wrote Rudolph the Red-Nosed Reindeer, but it wasn't him. Okay, and so part of his mission was, can you find a really simple mathematical system which gives rise to kind of chaotic behavior, so we can teach this in schools and get all of you guys interested? And the answer is yes, and this is it. So let's talk about bunnies. Aren't they cute? Here's a very cute bunny in a kind of, well, I'm not sure he's very happy because he's in a sort of, he's probably very hot in this knitted hat or something like this. But anyway, some cute bunnies. Trouble is, what do bunnies do? They eat, and well, they reproduce, because that's what bunnies do. So can we model what the next year's population of bunnies is going to be given this year's population of bunnies? So let's make this a bit more abstract. So what I'm going to do is I'm going to have my bunny population to be a number between 0 and 1. All right. So 1 means Watership Down, the maximum number of bunnies that I can possibly have. All right. Okay. I can't have more. If I have X equals 1, that's a disaster because there's not enough food. Everybody dies. Really, really sad. Obviously, if X is 0, it means the bunny apocalypse. All right. There's no more bunnies. So what's going to happen? Well, the bunnies next year, xn plus 1, well, that's clearly going to be proportional to the bunnies this year, because more bunnies, more randy bunnies, more baby bunnies. So, due to reproduction, the number of bunnies next year will be proportional to the number of bunnies this year. But unfortunately, if there are too many bunnies, that also means they're going to eat lots of food. So it's also going to be proportional to 1 minus the number of bunnies, all right? Because as x gets closer to 1, then we've got the possibility of starvation. So this is not so good. So what we're going to do, we're going to say, right, well, to combine those competing factors, let's just multiply them together. And then we'll have a model which incorporates growth and the possibility of starvation. And to turn that, we're going to have a little parameter called R, which I'm going to call the growth parameter. So we're going to vary that from 0 upwards, and we're going to see what happens next. So this is a quadratic equation, but it's in terms of last year's numbers. So this isn't something which is a continuous. This is a sort of discrete, iterative kind of thing. So what we're going to do is basically, and I'm going to use a spreadsheet initially for this, I'm going to define x from 0 to 1, and I'm going to see what happens. So here we go. Here's the spreadsheet. So look, numbers are a little bit small to see, but you'll see how it's color coded. So this is r equals 1. And what I've got in a spreadsheet, I've got, I think, 20 different possible values of x. All right. So here we go. So I'm looking at, 20 different bunny populations, 20 Watership Downs. Sorry, that's a sad one. That ends very badly. That's that story. So please don't cry. So there we go. So when x equals 1 or x equals 0, this is the iteration number, so different columns, then you can clearly see that that's 0. So, all the bunnies die. What about between x equals 0.05 and x equals 0.95? Well, unfortunately, this is not a nice story. So when r equals 1, basically the bunnies always die, sadly. So it always ends up, so after 18 iterations, we're down to a very small population. And what I've done is I've plotted all of these on a graph. So even when x starts at a high level, it kind of wiggles a bit and ends up something 0. So between 0 and 1, that's quite sad, unfortunately. Right, what about bigger than 1? Well, here's r equals 2. Now, this is interesting. So regardless where we are, apart from 0 and 1, the bunny population tends to an equilibrium value. All right, and it depends on the value of r, but in this particular case, it's actually a half. So when r equals 2, we end up with, somewhere in the middle. All right, it always ends up at 0.5. Oh, that's interesting, you might think. All right, what about when r equals 3? Well, now we start to see some interesting behavior. So now we don't have a fixed population at all. So it's kind of hard to see. And I actually, in my book, I've kind of color coded this. I'm afraid you haven't got those slides. But basically, if you look at the graph, it's easier to see. You can see a sort of oscillation between a sort of high and a low population every year. All right, interesting. What happens if we keep increasing r? Well, you get to r equals 4 and it's complete chaos. Really hard to predict. Long term, you get some really wiggly, mad graphs with all sorts of ups and downs. And if you were to say, right, in 100 iterations time, what's it going to be? Anybody's guess. All right. So you're almost introducing random behavior. It isn't random because we've got a law which is completely deterministic. All right. It's a quadratic equation. But nonetheless, we've got very complicated behavior ensuing. So here's an idea. So we've got the situation where the time history, x versus time, is quite sensitive depending on what we started with and indeed this growth parameter. So in most of physics, we like to say, right, okay, I've got a spring, I've got a magnet on a spring and it wiggles, what's going to happen next? What's the position t seconds in the future? All right, I've got some, I know, little ball bearings or cars colliding with each other. What's going to happen next? Right? This is actually not a great answer. This is not a good situation because when r is 4, that's really difficult. It's a completely different curve. The blue curve is totally different to the kind of orangey looking one. All right. So this is not the right representation of what's going on. So we need a different view. And this is kind of like a trope of chaos theory. So what we do is this. Rather than plotting just one trajectory versus time, we plot all of them. So let me just explain this graph because it's this is quite cool. So basically, what you do is you say, all right, I'm going to start with loads of possible starting values of x, and I'm going to run it for maybe 2,000 iterations. So not 20, but 2,000. So I've done this with a computer. All right, so I work out 2,000 iterations, and I then plot the next 2000 values just on the same graph. So there's no time here. I basically plot them on a graph, and this is what I get. So what you find is for the second 2000 iterations, when R is between 0 and 1, it's all on there. It's extinction, the bunny apocalypse. If R is big between 1 and 3, you end up on this green line. So wherever you are, it's all 2000 points when R equals 2 will be right where my mouse pointer is. All 2000 points when R equals 1.5 will be about there. Okay, so underneath this is a really dense splodge of eventual values because they all end up at the same place. Now, once you get above 3, we bifurcate. So what will be happening is, say that R equals, I don't know, about 3.2. Alternately, you'd be going there and there and there and there and there and there, right? You'll be bouncing between two values. So you don't want to be plotting the time history at all. You just want to plot, the last 2000 points. And then something really interesting happens. So once you get to about 3 point, it's this point here, 1 plus root 6, as it turns out. And that's a really cool calculation to do. You'll have to read Science by Sim 1 to get into that. But basically, you can work out where these bifurcation points are. And I've done it for the sort of end of the blue curve. In fact, this is the blue curve. Beyond that, it's a bit hard. So there's a book by Strogatz, which might give you a recipe, but it gets progressively trickier to work out these bifurcation points. And then you have absolute chaos. But within this chaos, you see structure. You'll notice there's some white lines here. So if you zoom in, all right. Oh, by the way, this is the sort of computer simulation. So that's 2 solutions, so that you get a kind of basically a time history here. The different colors are the different starting points. You can sort of see they're ending up. And I might see if I can actually load this. Just get out of this and load up MATLAB. Bear with me. Might be able to do this dynamically. Let's go back to our simulation. Oops. There you go. So if you zoom in, so right in that corner here, if I zoom in, you get this. So this is why you need a computer program to work out lots of trajectories all at once. And what you find is, as you zoom in, it looks a bit like the big picture. And if you zoom in again, it looks like the big picture. So this is what we call a fractal. Something where, so a fractal geometry is where it's a bit like mountains and rocks. If you take a mountain range and you then take a rock from the mountain, it looks a bit like the mountain. And if you stick the rock under a microscope, it looks a bit like the rock, right? Which looks like the mountain. And you can kind of keep going until you get to the atomic level, and then it's a bit different. All right. So this is a sort of fractal structure that at every scale, it kind of looks the same, self-similarity. So amazingly, this sort of fractal structure is related to this very simple bunny sort of population model that we get. And all we have to do is get the right representation. So just to be clear again, is that what we're doing is we're saying, depending on my growth parameter, in this case, it's 3.54 to 3.66. What I do is I have a random start values between 0 and 1. I run it for 2000 iterations, and then I plot the next 2000 on a graph, and this is what I get. So there we go. In fact, if you take this, you can actually work out the probability of it being within a certain range. And so I don't know if this comes across, but there's certainty for your the first bit when R equals 1. And then, oh, actually, no, this is a zoom. Yeah, so this is a zoom, actually, not just at this. So this is sort of within that tiny region. So you've got certainty here, and then you've got a bifurcation, and then it becomes really low probability. It's completely chaotic. So you have order, chaos at every scale within this structure. So this amazingly complex structure comes from just a basic quadratic equation. Fantastic, isn't it? So there we go. So before we might look at another, perhaps another one or other model. I'll see if I can actually run a little simulation live for this. So you can download all of these from my website, from the Eclecticon, and I think we'll go for, see if we can find it. Loops, roots, and chaos. There we go. So maze bifurcations. I think it might be this one. Let's have a little look. Let's have a look. Yeah, there we go. So here, here's my logistical map. And I don't know if I can actually, I'm not sure I can, hello. Let's see, is this getting out? Oh, whoops, I've done something bad here. I don't think, right, bear with me. Right, let's go for, right, I might have to go and cancel that. Yeah, sorry, I think it's not working very well with my my screen. So I'm just going to quit MATLAB. Let's just get rid of that one. End task. There we go. I think I've got a more dynamic version. Am I still broadcasting, by the way? That didn't take out the line.
Yes.
It's all good. Right. So I'll see if I can load that. I've got one which you can move a mouse pointer, and you can kind of see this going. All right. Let's have a look. So maze bifurcations. I think it's made with key press. Right. There we go. So yeah, there we are. I don't know quite why I'm not seeing it all on here. Yeah, it's because I've got to strain my screen resolution. Bear with me. Right, let's go for display settings. Right, so let's go for. Right, okay, here we go. All right, is that still coming across okay, everybody?
Yeah, I think so.
Yeah, I'm not getting the title on this for some reason. Right, so basically what I can do, I don't know why I'm not getting R on this particular model. Yeah, it's giving it sort of. Oops. Yeah, I've got some resolution problems here. Oh, there we go. That's the issue. Yeah, I've got there's a bug in this program. Sorry about that. So what we've got, I don't know why it's not giving me the title, but this is where I've got the sort of, I can use my keys here to work out. So there's my, so what I've got here, this is for small values of R. And this is where I end up. Basically, this is sort of time. And I've got different values of my initial X position, and they end up at an equilibrium value. And as I increase my growth parameter, my equilibrium value changes and gets larger. And then suddenly we get a bifurcation. And then we get bifurcations of bifurcations, and eventually chaos. There we go. I don't know if I've got, if this one runs. Yeah, I don't know if I can move this. This is slightly annoying. Yeah. Yeah, there's something with my display saying, I think it's the Zoom is affecting it. Sorry about this. We'll have to go back. I'll have to test this again. But basically, I've got one that you can sort of zoom in directly. Yeah, I will have to check that myself. Sorry about that. Never mind. So there we go. You don't win all the time. Right. Okay. So what we'll have a look at, I'm just going to show you a little picture. This is a double pendulum. I think it's best if I just show you a little video of this one. Double pendulums are surprisingly complicated. So I've got a little this one here. So if we look at this one, here we go. So here is a double pendulum. Is this coming across all right, Robin?
Yes, yeah.
So what you've got is you've got a sort of a little mass here. So the bottom mass is 1 kilogram. The blue one's 3 kilograms. And I've gone for some enormous dimensions. So the first distance is 3 meters. The second distance is 2. All right. So, and yeah, it's swinging around. There's a bit of movement going on. But what happens if we put this right at the top? So there we go. And now, with just a small change in parameters, we can get all sorts of really complicated behavior. So it swings, it almost goes backwards, almost sort of defying gravity. The middle one's sort of spinning around. And you might ask the question, how do you work out what happens next? What do you plot? And Honoré Poincaré basically says, well, the time history, a bit like the maze situation, is not what you want. Okay, so basically what you want is a phase plot. So rather than plotting versus time, you might plot the angular speed versus the angle. So if I'll just skip ahead to where that is. So here we go. So this is what we call a phase portrait. So if you have just a normal pendulum, not like a double pendulum, but a single one. Here we go. It's a bob here, sort of moving. And if you do Newton's law, you get simple harmonic motion. So again, look at that in slow time. But the idea is that you can look at the rate of change of angle, or the rate of the angular acceleration is proportional to the angle change itself. And you get sort of harmonic solutions as the pendulum bob moves from one side to the other. So if you plot it, so you can plot that versus time, and you get some sort of sine or cosinusoids here. But what you really want to do is plot the angular speed versus the angle. And to make it sort of scalable, if you do angular speed over 2 pi versus angle in radians, what you'll get is a circle for simple harmonic motion. But as you get air resistance, it will start to spiral inwards. And not all of these are symmetric. So for your pendulum, you might have a model of drag and air resistance. So you can kind of use the same idea, but for the double pendulum. And there is some hardcore maths here. So I'm going to just skip the answer. So this is the sort of your pendulum trajectories. But if we go for the situation, this is the sort of simple one, so that you've seen. But if we make it more complicated, where we are, let's go for this sort of chaotic version. So for the early one is what we saw, where they were nice, swinging backwards and forwards. One of them was slightly larger in amplitude than the other one, the red one. So it all looks very regular so far. Now, if we go for the chaotic version, and that's its angular velocity versus angle diagram, it's a kind of pretty picture, but nonetheless very regular. Whereas for the chaotic version, let's remind ourselves that again, that's this one here. What you find is that the pendulum here, the red one, occupies a whole range of possible parameters of angular speed and angle, but not all. And if I bring it up, you can kind of see it. So there we go. So I've plotted the X and Y trajectories on a little picture. So you record the time history. And if you plot the angles, it looks very, very complicated. There's all sorts of wiggles involved. So it's not so easy to sort of try and predict what what's going to happen here. What you really want is something which you take time out of the representation. So there we go. So this is what we call the phase diagram, the Poincare diagram. And what you can see, there's a blue pendulum blob, and there's the red one. And the red one occupies all sorts of regions, but there are regions where it never goes. So large angles with large angular velocity, for example. And within here, you've got these sort of areas where there's sort of islands of stability. So this is, if you're analyzing systems, plotting a phase portrait with maybe a speed or an angular speed versus an angle gives you a much better idea about what the full motion is going to be. And they also look quite aesthetic as well. So that's a kind of idea. So we've seen this sort of sense of not plotting what happens versus time, but something else, something visual, where we're putting all the trajectories in one place. And that's a sort of a chaos trope. I think the last thing we'll do, do we have any questions, by the way, before we, I'll show you one more thing. Nope.
No, all good.
All good. So let's have a little look. What I think we'll pick to finish off. Yes. So I think this will be a nice thing to sort of to finish off. Is we're going to look at this idea called the strange attractor. And so this is the story. This is Edward Lorenz. I think that might be Edward Lorenz. Anyway, and that's not a modern computer. This is a Royal McBee LGP30, which was state of the art in 1961. And so he was using this to model weather patterns. So never mind where these came from, but basically it was something to do with atmospheric pressure and a sort of sense of. So imagine if you're looking at the weather, you want pressure, wind speed, temperature, humidity, that kind of stuff. And you've got those measurements, with height and also with sort of latitude and longitude. And the Met Office will have this amazingly complicated model where you're trying to predict what those things are going to be, days and maybe even weeks ahead using supercomputers. So in Reading or in the Met Office in Exeter. And so he was basically doing something like this. Now, it's not really sort of clear, what X and Y and Z mean, but they are going to be related to pressure, temperature, etc. So essentially, he created a series of equations that looked a bit like this. And so we can kind of think about an X, Y, Z space and how the sort of weather parameters can be plotted as trajectories in X, Y, Z. And so you can't use calculus to integrate these. You have to use a computer. And the sort of simplest thing you could do is you could say, well, let's look at a small time interval. And if we know what X and Y are and Z are initially, we can multiply that by a change in time and work out the change in X, etc. So he did this in a computer. And what he did is he thought, well, this took a long time. And so when he got to the data the next day, he just fed in where he got to and sort of see what would happen next. And what he discovered is he got completely different weather. So, he got some really wild solutions. And it turns out that he'd been not putting the right number of decimal places in. I think the computer worked to 3. Yes, we worked to 6 digits of precision, and he fed in 3 and got completely different weather. So this is a bit like when you've got your pool cue and you hit a ball and you're slightly out and you get totally different results. So these equations lurking within them, because they're non-linear, it's an XY term here, you get wildness. So, and this turns out to be a very general phenomena. And so what he decided to do was plot what X and Y and Z look like. And you end up with this. This is called the Lorentz attractor. And essentially, what does that mean? It means, well, although the trajectories themselves are very, very sort of chaotic. So I've plotted a few of them, as each color is a different trajectory from a random starting position. But nonetheless, there is some structure. And what you find is that a bit like sort of, for the maze bifurcations, that sort of certain growth parameters, you end up at a certain kind of equilibrium value. You're not in equilibrium here, but your trajectory ends up in this sort of butterfly-like structure that exists in X, Y, Z. And that seems to attract the trajectories. So you get a different butterfly depending on what these S, R, and B parameters are. It's a bit exotic why I've chosen these numbers. But that's sort of from Shaw's book. But basically, once you fix those parameters, you've got the same kind of set of equations. It doesn't matter where you start, you end up somewhere on this. So that may sound a bit unbelievable. So we need an animation to show this. And one of our fantastic students has actually done this. That's a part of our Cambridge course. So you will do this in future. And this is a picture from Shaw et al. In 1986. And what they've plotted the Lorentz attractor. But to kind of make sense, they've got a little tiny blob of dye. I don't know if I can zoom in here so you can kind of see right in the top. But basically, this little blob of dye here are maybe 1,000 data points with very tiny differences in X, Y, and Z. What you do is you work out those trajectories and what happens next. And what you find is they end up spreading all around the Lorentz attractor. So let's go and look at a little film of this. And here we go. Here's one I made earlier. And so you can see the little red blob whizzing round one of these trajectories. And about now, it starts to spread out. Now it's on the other side. And now all sorts of craziness starts to happen. It's like one of the Matrix films, one of the kind of the robots that attack the humans in the center of the earth. Now we've got some sort of tendrils. And what's happening is that my initial conditions, which were very, very small and random, now result in trajectories that are all over now, spread around the Lorentz attractor. So we've got very, very high sensitivity to initial conditions, but nonetheless, we do have some structure here. It's not randomness, all right? There is order to our chaos. It just depends on what we're talking about when we plot it. Let's just plot that one more time. And there we go. So there we go. There's our starting condition. It's moving around one of those trajectories because it's pretty much the same starting point. But now there's small differences in my starting point mean I end up in all sorts of different places around this Lorentz attractor. So what I'm plotting in the green is a trajectory I can't remember if I've overlaid several trajectories or just one over many. I think it's just one trajectory, but for a long time. So you can sort of see how it ends up. So it attracts, in some sense, what's happening to my particles. So there we go. There are a lot more tropes and ideas that come into the umbrella of chaos theory, but this kind of illustrates some simple things. So what are the kind of ideas that we got? Simple. We've got a rule. In this case, I know exactly what's going to happen next based on my differential equations. So I know what's going to happen with x, y, and z. I've got it in terms of velocities, but I've got an equation for it. But what happens next is very, very sensitive to my initial values of x, y, and z at t equals 0. But nonetheless, in this situation, it doesn't just happen randomly. It will sort of collect the result in a certain structure. So if you know what the structure is, perhaps that tells you something more fundamental about what's going to happen next. I think I will probably end there, unless we've got any more questions about this or about the challenge itself. We'll see you next week, I think, for the final one. So thank you very much indeed, and yeah, we'll see you next time.